Can everybody hear me on the Zoom? I assume you can. Okay. All right. So let me introduce our speaker for today. Our speaker today is Professor Ingancio Franco from the Chemistry Department of the University of Rochester. Yeah, it's a pleasure to have him here. I know him personally for a while. It's always nice, and he's done some very good work. This work was published, I think, in Nature last year. Okay. So Ingancio from National University of Columbia, and from there he made a big jump to for PhD from Toronto University of Toronto in Canada. That's where he went for a PhD. After finishing PhD, he did a postdoc at Northwestern University. And from there, he found a fellowship, a Humboldt Fellowship in Berlin. That's where he worked for a while, a couple of years. And then he joined the chemistry department here in 2013. And became an associate professor about 2 years ago. He has got several awards already. He's outstanding junior faculty award of American Chemistry Society and Curtis Teaching Award of the UFR. Also from the college here, he got the Undergraduate Teaching and Mentoring Award. And also a few years ago, I remember he got a Mendel Faculty Fellowship in this department. So he's doing great. With that, let me get you over here. Good.
Okay, so let me start thanking you all here for, all of you will be here. I'm sure that it's not only about the cookies, but the cookies are better than this church, for sure. And thank you, Gavin, for this opportunity to address this community and to tell you about some of the work that we're doing that I think is quite related to things that are happening in this department next door in Hutchinson Park. And in particular, I would like to focus today on our efforts to introduce methods to control matter at the level of electrons on ultrafast timescales. Let me start by saying something that I really care about is the idea that molecules and materials are pretty amazing quantum systems. They have manifolds of transitions in many regions of the electromagnetic spectrum, this, infrared, microwave, and so on and so forth. These energy levels can be chemically tuned. You can assemble them into complex architectures. They're really pretty amazing. And for this reason, essentially, since the inception of quantum mechanics, a long-standing dream in chemistry, and to some extent in material science, is how do we use quantum coherence and other non-trivial quantum mechanical effects to enhance molecular function. So pretty much along these lines, in my work here at the University of Rochester, my group, we do theory and simulation, and we care very much about quantum frontiers of molecular and material science. So right now, topics that we're advancing at this time are the idea of how do we control matter at the level of electrons using ultrafast laser sources, and this will be the subject of today's lecture. Because we're interested in quantum control, we are also very interested in the quantum coherence of matter, and in particular, how do we protect that coherence? How do we model it? How does the decoherence occur? So this is a big topic in my group right now. Because we have to deal with these problems, we have to somehow be able to put them in a computer. So we work on quantum simulation, we develop theories and computational methodologies to capture the quantum dynamics of molecules and materials, both in classical computers and more recently in digital, in analog and digital quantum computers. Another topic that is very interesting to us is the problem of quantum transport. And all these other topics, I will leave them for another time. Okay. So the topic of today's lecture is the problem of how do we control matter at the level of electrons. The reason why we focus on electrons is because if you control electrons, then you control the optical properties of matter, the ability of matter to transport charge, and eventually its chemical reactivity. And the reason why we choose lasers to control electrons instead of conventional means, and by conventional means, something like an applied voltage or thermodynamic control or even chemical control, is because if you're able to do it with lasers, you're able to do it very fast on femtosecond timescales. And this is something that you cannot achieve by any other means. And what I would like to do today in that last step, let me just try to get rid of of the title such that you can see my screen. What I would like to tell you about today is this very interesting phenomenon in which we are able to control charge carriers, both real and virtual, and I will tell you what this means. And through that, this augmented control landscape led us to information processing that operates now at the petahertz limit. So we're really working toward pushing electronics toward the petahertz, which is about 6 orders of magnitude faster than the current state of the art. So in addition to the laser-induced currents along nanojunctions, which will be the main subject of today's lecture, there are other strategies for control electrons that we have developed over the years. There is a general strategy based on the Stark effect that we call shelling, and if we have time, we will talk a little bit about this. And we have also been working quite heavily, this is a topic that we are heavily invested right now, in the blockade engineering of the material properties, and in particular optical properties. But let's begin with laser-induced currents and laser-induced spatial symmetry breaking. So the system that I have in mind is a junction in which this is gold, this is some material, and that is gold. There is no bias voltage. The system is spatially symmetric. The material can be a semiconductor, it can be a dielectric, it can be a semi-metal, it can be a molecule, right? It can be many things. And what we're going to do is that we're going to shine light on this junction, this very special class of laser fields, and we're going to break the spatial symmetry and generate currents. And if you're able to do so, then we'll be able to induce currents or bursts of currents on femtosecond timescales in the absence of bias voltage. This is the phenomenon of laser-induced spatial symmetry breaking. And by doing so, we will have essentially a new current standard. What do you need for this? So there are essentially two physical requirements that you need to generate these bursts of currents. The first one is that you need a light that is on low temporal symmetry, and I will tell you about that. And you need the nonlinear response of matter to this laser field of low temporal symmetry. And the traditional example is a field that has two frequency components. This is the electric field of light, and you have a frequency component omega and another one, which is the second harmonic to omega. So you shine this type of light to matter to stutter in the response. Once you average over time, you get 0 because this is an AC source. It has 0 temporal mean. The second order response is also 0 because you have a system that is spatially symmetric. So that second order response is 0. And the first response that is non-zero on average in time will be the third order. So if you take this laser field and you cube it, you take the third order response and you just time average, and that line is supposed to mean a time average, what happens is that you get this phenomenon of harmonic mixing that you know, that I'm sure that you all know very well, in which the frequencies of the field start to mix together because of the nonlinear response of matter to that laser field. So you may have processes, for example, in which you have two of the omegas coming from this part of the laser field, omega plus omega, and then another of the omegas coming from this other component of the laser field, minus 2 omega, to get a 0 frequency component in the response. And that 0 frequency component in the response, what it's doing is that it's generating either net dipoles or currents that survive time averaging. And what is very important about this is that just by changing the shape of the laser field, by changing the phases, or in particular the relative phase between the 2 omega and the omega component, you can determine, you can control the magnitude of the spot-induced dipoles or the currents that you generate. So this is a very general phenomenon, and it's been known for maybe already 30 years. It's not something new. But experiments are no longer done with this type of laser fields, omega and 2 omega. How experiments are done right now is that instead of using these continuous wave fields with two frequency components, what they use is fields that are extremely short. So short, these are optical fields, 1.7 electron volts as the photon energy, and they're so short that they actually only a few cycles. They only have a few cycles. So this is the electric field as a function of time, and these are actual measurements of the electric field in black. You see that they only have a few cycles within the envelope of this laser. The reason why we want to use few cycle lasers for the control is because now you can really crank up the intensity of that laser field without inducing the electric breakdown, because the interaction between light and matter is is for a very short amount of time. So you can access a regime, a non-perturbative regime of the light-matter interaction, something that you cannot capture by finite order perturbation theory, and before inducing the electric breakdown. The electric fields that you can now apply with such few cycle laser pulses are electric fields of the order of amplitudes of 0.1 to 2 volts per Armstrong, or intensities of 10 to the 11 to 10 to the 13 watts over square centimeter. And this type of light-matter interactions, what they do is that you are in a regime, it's an intermediate regime of the light-matter interaction, which is non-perturbative. The light-matter interaction is comparable to the strength of the chemical bonds, so you're completely distorting the electronic structure properties of materials, but you're not ripping electrons apart. You are not ionizing. No? So you are dressing the material, you're distorting its electronic structure. You're creating essentially a new material, but you're not ionizing it, or you're not doing dielectric break. Now, the control that you can achieve with such laser fields is on a femto 2 attosecond timescale. The femtosecond is easy to see because your whole laser field is just maybe around 7 femtoseconds, maybe 10 femtoseconds or so. But the reason why you can actually go and control matter on attosecond timescales is because what happens when you have such strong laser fields is that the response of matter to that laser field is not due to the envelope, like in gravity physics, what you have is the response to the envelope. And in here, you're actually responding to the instantaneous value of the electric field. So your matter is actually seeing the whole structure of light. And then if you have a phenomenon that requires that particular amplitude of the laser field to respond, maybe your whole control occurs because of this little peak in the laser field. And because of this, you can actually go to attosecond type of control. Another aspect that we're very interested about few cycle lasers is because you can actually induce non-trivial Stark effects. So I don't know, but I come from the molecular world, and Stark effects is something that is small, maybe electron volts or something like this. But with this type of laser fields, you can actually have Stark effects that are so large that you can turn a few silica, so a dielectric with a 9 electron volt energy gap, into a metal for a very short amount of time. So they completely distort the nature of the material. Now, when you control, the way to think about these laser fields in an approximate way is essentially that you have some envelope. Hopefully, if you're good, you have a Gaussian envelope. And then that electric field will be that Gaussian envelope times a constant function with a central frequency omega and this phase. And this phase is called the carrier envelope phase. When I was a PhD student, controlling the carrier envelope phase was science fiction, no? But now all the newest experiments are actually using this to manipulate the electrons in matter. And I'll tell you why this is the case. So what the experiments do is that they control this carrier envelope phase. And by changing the carrier envelope phase, what you're doing is that you're changing the shape of that electric field. In fact, for some carrier envelope phases, this would be a challenge, but let me try. For some carrier envelope phases, you may be in a situation like this, in which your field is symmetric with respect to time inversion, with respect to time zero. Yeah, but that's a phase of zero. But for other carrier envelope phases, you may be in situations like this, where your laser field is antisymmetric with respect to time inversion. Yeah, and it turns out that these temporal symmetries or lack of temporal symmetries will have profound effects on the type of control that you will be able to get. I will argue that the first proposal to use the sub-cycle structure of light to control electrons along nanojunctions was done by me as a PhD student, the dream of a PhD student. And it was really a dream because at the time in which I was thinking about this, it wasn't clear whether you could create such a junctions. It was not clear that you could isolate the signal of the material part that you care about, the molecule in that case, from the gold, because the gold are essentially perfect chromophores. And it wasn't clear whether you will be able to see something before actually breaking this whole junction. So it took years for the first experiment to emerge, and the first experiment was done by the group of Ferenc Krauss in the APQ, an experiment that changed my life. And what they did is that they actually, their junction is silicon dioxide connected to metal gold, and they use a few cycles structure of light with a polarization across this direction. And in that process, they generate currents that they can manipulate by varying the Carrier envelopes. And after that paper appeared, we spent here, this was a big paper in my tenure track years here at the University of Rochester, and really understanding every single aspect of that experiment, trying to simulate it, to understand the signal of why did it work, why didn't it work, and our perspective on those simulations are summarized in these papers that we published a few years ago. And since then, I wouldn't say that there has been explosive progress, but it has been important progress in the control of currents with these few cycle structures. There may be around 20 labs around the world that are doing experiments in this direction. There is the second generation of experiments by Peter Homenhoff. Here's my main collaborator, and they're doing basically graphene connected to gold. And by the same type of thing, few cycle structure of light that is inducing currents along these graphene gold structures. There are people not only in Europe, but also here in the US, in Michigan State, in which what they're doing is that they have a surface, a metallic surface, and they have a metallic tip. And now they come in with this is not visible light, but this is terahertz radiation, and with that terahertz radiation, they generate bursts of currents in this STM type of setup, and in that process, they can now image nuclear motion and molecular motion on femtosecond. This is also very interesting. There are effects in which they use the structure of gold as an antenna, in which you will modify the structure of light and amplify it, and then use it to do control of electrons in nanojunctions by using much weaker laser sources. There are schemes to measure electronic coherence that are proposed based on this idea. So these are examples of experiments that are happening right now in this field. So what I want to tell you in this main part of my talk is the result of a collaboration, one of the great collaborations of my life, in which every person in this collaboration contributed in unique ways. And we got to a place in which none of us could have gone individually. No? So the work that I'll be describing is a collaboration between Antonio Garzón, who was a student in my group, a PhD student in my group, that did all the computations that I'm going to present. And this was the main paper of his PhD work. And the group of Peter Homenhoff at Erlangen, and in particular Tobias Bulaki and Kristen Heide, which were at that point PhD students in the group. So here's our hypothesis. And the way that I like to do science is that I like to start with a good hypothesis. So this was the hypothesis. So this is all in the context of junctions that are based on gold connected to graphene and then gold. And the hypothesis is that there are two types of charge carriers that you can generate. What we call the real charge carriers, I'll explain, and the virtual charge carriers. And that depending on the shape of the laser field that you use, you will either be able to generate the real or the virtual. In particular, if your field is antisymmetric with respect to time inversion, something that looks like this, for that you need a carrier envelope phase of pi halves. You will generate only real charge carriers. While if your field is symmetric with respect to time inversion, something that looks like this, for that you need a carrier envelope phase of 0, you will generate only virtual charge. That was the hypothesis. And I'll tell you what the evidence for this is. What this means. The real. So the real is your regular photo excitation. You come in with your laser field, you generate electron hole pairs. These electron hole pairs remain excited after the laser field is done, so your material remains excited. Because your laser field has a low temporal symmetry, because it has this few cycle structure of light, what happens is that you give a kick to these electrons and holes. So the electron will move in one direction, the hole will move in the other direction. They will travel through the material, through the graphene, And eventually they're collected by the gold and they generate a current. That's a regular photoexcitation that we know. The virtual. So this is another component of the response of matter to light. So when you, I don't know how many, I'm sure that all of you have solved the time-dependent Schrodinger equation, but when you solve the time-dependent Schrodinger equation in the presence of a laser, even if your field is non-resonant, if you look at populations of your states, they will be occupied transiently during the pulse. So these are called transient excitations. Once your laser field is done, because your response is non-resonant, all those transient populations decay, no? Because you don't have the conservation of energy to have net photon absorption. Okay, so in a similar way, if you have these laser fields, what these laser fields are doing is that they're generating a polarization response. They're generating a net dipole. And you see, for this carrying below phase, that electric field is more intense for, say, positive amplitudes than for negative amplitudes. And because we are thinking about the nonlinear response of matter to such fields, that means that my electronic cloud that I'm shaking back and forth will move more in one direction than the other one. That is, during the pulse, I will generate a net dipole. Yeah, that's something that survives time averaging. After the pulse is done, nothing happens. I go back to where I was, no? Because it's sort of like a non-resonant component of your response. So we call these virtual charge carriers because they only exist during photoexcitation. Yeah, they only exist transiently during photoexcitation due to this polarization response. And if I just had the graphene and did this, well, sure, I would have a net dipole during my laser field, but once my laser field is done, I would go back to where I was and game over. But in these experiments, what we have are goals, no, at the boundaries of this graphene. Yeah. So what happens is that you generate this transient dipole during the laser pulse, but because you're connected to the goal, that transient dipole actually gets rectified into a current. It gets to form a current. What was the evidence for this? So there were two pieces of evidence when I started to do this. Well, I mean, there was a symmetry analysis that I created many years ago, in which essentially what I had discovered is that if you had a field that was symmetric with respect to time inversion, for example, something that looks like this, what I knew is that you could not generate net momentum that will survive time averaging. And for this, in the photoexcitation, for me, this meant that no real charge carriers were possible. But if I had a field that is antisymmetric with respect to time inversion, what I knew from the symmetry analysis was that I could not generate a net dipole that will survive time averaging, the double bar time average. For me, this meant that no virtual charge carriers were possible. There were issues. This whole proof is based for continuous wave type of excitation where your laser field is constantly on, and for closed systems. And these experiments were done in completely different systems, in completely different regimes of the light-matter interactions, because these were with few cycle lasers and open quantum systems. So who knows if the symmetry analysis was applicable? Okay, then there were two experiments. There was the experiment in gold, silica gold. And in this particular case, this is the type of control that they get. So they don't plot the current, but they plot the charge that they extract out of the experiment. So the integrated current. So this is the charge that they extract out of the experiment as a function of the carrier envelope phase. And what you should be looking at is the squares. And what you see is that the maximum of the control is right at the phase of 0. While if you change so this is the maximum of the control is right at the phase of 0. Oh, that's important. Of course, if you change that phase, you change the direction and magnitude. And there was a second generation of experiments done in gold, graphene gold. So while these experiments, they have 15 nanometer nanojunctions, these experiments in gold, graphene gold, they're with much longer nanojunctions. It's not longer nanojunctions, but microjunctions, because these are, the graphene is about 5 micrometers in wide. And what they like to plot are the results, they like to plot them in this particular way. in which radially they increase the amplitude of the laser field from 0 to 1 to 2 to 3 volts per nanometer. And if the current is positive, they plot it in red. If the current is negative, they plot it in blue. And as you go in this direction, what they plot is the carrier envelope phase of that laser. And what you see is that the maximum that control that they get is at a phase of pi halves or 3 pi halves, which is very different than the one that they were observing in gold silica gold nanojunctions. So two very related experiments with two completely different signatures for the phase. No? And we wanted to know exactly what was going on. So remember meetings in person, but this was a very important meeting for me because we had spent about 3 years doing simulation work on the gold silica gold nanojunctions. And the group of Peter Helmholtz has spent about 3 years doing their experiments in gold graphene gold nanojunctions. And then we realized that we were thinking about the same things, but they were doing experiments and we were doing theory. And we sat down and in an afternoon in this meeting, we formulated this hypothesis, and this led to many years of collaborative work with him and a collaboration that is still ongoing. So from a theory perspective, in order for you to be able to capture both the real and the virtual, what you need to be able to do is you need to capture the quantum dynamics of electrons in this graphene in bulk, no? But you also need to be able to capture interfacial effects. There are several calculations out there in the literature in which they only consider these junctions as bulk, and they're missing these whole interfacial effects. And from my perspective, they're missing a substantial chunk, if not a dominant sometimes, component of the physics. So the way to do this is by these methods that are called the time-dependent non-Euclidean Green function methods. And essentially, what this allows you to do is to solve the Liouville-von equation for electrons in these nanostructures, in which you have the unitary dynamics that is driven by your laser field, and then you have these additional terms that essentially extract charge from your graphene, and then is captured by the gold, and then the gold replenishes the charge back into the system. And so this is the open quantum system part of this type of simulations. So I'm going to show you now 4 years of simulation work in one slide. Okay. So this is work by Antonio. And what Antonio did is the following. He set up a calculation in which we have graphene nanoribbons coupled to metallic contacts. The experiments are done in full graphene, but we cannot do full graphene with these boundary conditions. So we have to do it with graphene nanoribbons. Sure, we make sure that the graphene nanoribbons are metallic or semi-metallic as the actual graph. And he has a fixed width, and then the length is varying. So he has 3 lengths: 21 nanometers, 42 nanometers, and 85 nanometers. This is the electric field as a function of time, and this is the charge that you can extract as a function of time. And he considers a carrier envelope phase of pi halves and of 0. He doesn't, what we plot here is not the current, but is the integrated current, so the charge that you extract out of this junction. So let me focus first on the carrier envelope phase of pi halves. So you see, during the laser field, charge moves back and forth from the left to the right with the laser. But that makes sense because your laser is just driving your electronic cloud in one direction or the other. Just after the laser field, you have not extracted very much charge or nothing at all. But once your laser field is done, what you see is that your charge starts to increase linearly in time, and then it sort of bounces back, it restores, and then it oscillates, and eventually it settles. So what's happening? You shine your laser field, you create your electron-hole pairs. Your electrons and hole are traveling in opposite directions. As these electrons and holes are being captured, this is when you see that this charge is increasing linearly in time. Yeah. But some of that cloud, some of that electronic wave packet and Hall wave packet will bounce back at the interface. Not all of it will be absorbed. And because it bounces back, then you see that the charge eventually goes in the other direction, that's the bouncing back, and then it oscillates and eventually it sits. If you go from a small junction to a long junction, so the small junction is the black, the medium-sized junction is the red, and the longer one is the blue. What you see is that, well, first of all, the initial launch is much bigger. The effect is much bigger, the bigger the junction. And the reason for this is because the photoactive space of your junction is larger. Okay? But the other thing that you see is that the oscillations in the smaller junctions are faster. And this is also easy to understand because that is the time that it takes the electrons to bounce back and forth in these nanojunctions. Okay. But I want to say, the electron wave packet is launched after the pulse. All the action that you're getting is after the pulse. Yeah? The magnitude of the effect increases with length. The larger the system, the larger the photoactive area, the larger the effect. And a net charge that is extracted during the laser pulse. And all these characteristics are exactly what we mean by real charge carriers. This is the phenomenon that we discussed.
This is similar to what we call in optics Fabry-Perot. A Fabry-Perot interferometer optics behaves in this way.
Yes, but a very poor Fabry-Perot. So very lots of dephasing and issues. Now, the only thing that we do, same setup, exactly the same thing. But we change the phase of the laser to a variable phase of 0, from 5/2 to 0. And this is what we're doing. This is the charge as a function of time, identical setup otherwise. So the first thing that you see is that you get the control only during the laser pulse. All the action is during the laser pulse. After the laser pulse is done, not much goes on. Yeah. So this tells you that whatever is happening is due to whatever excitations you're generating during the laser pulse on. The other thing that you see is that this is independent of length. And the reason for this is that it's an interfacial effect. So it doesn't matter how large your system is to a certain extent. Your effect will be approximately independent of systems. For reasons that I don't have the time to discuss today, this effect is actually robust to decoherence, while this other one is actually a little bit sensitive or very sensitive to decoherence. But this is exactly what we mean by the virtual charge carriers. The control is exactly during the pulse. No charge carriers are present after the pulse. They're all due to virtual charge carriers. They're independent of length and for reasons that I didn't discuss, it's robust to decoherence. If there is any truth to this, then what we should see is that if I go from a long junction to increasingly smaller junctions, for the longer junction, the real charge carrier should dominate because they increase with system size. And as I make my junction smaller and smaller and smaller, this effect should become weaker and weaker and weaker. This effect hopefully will be approximately constant. And with a little bit of luck, we should see a change in the control phase from the variable phase of 5/2 to 0 if we're changing mechanism. So based on these calculations, this is exactly the experiment that was done on Erlangen. And so what they did is that they created 3 junctions, one with 5 micrometer, another one with 2 micrometer, and another one with 1 micrometer. And what they plot again is the electron-disc plots in which the amplitude of the laser field increases radially from 0 to 1 to 2 to 3 volts per nanometer. And the magnitude of the current is plotted in red for positive direction, in blue for negative direction. And the phase of the laser field is plotted radially like this. So you see, for the 5 micrometer junction, what they get is that the maximum current occurs at a current phase of 5/2. This is what they knew before. This was the experiment that this group had done before. But as they decreased the size of the junction from 5 to 2 to 1 micrometer, they started to see a shift in that maximum of the control all the way to pi. So what you were seeing is a change in the mechanism from the real charge carriers to the virtual charge carriers. We were very excited about this because we had discovered these 2 mechanisms for the currents, and then we realized that we could disentangle these 2 mechanisms and activate individually just by choosing the phase of the laser that we use for the photoexcitation. So we sent this to a nice journal, and 2 days before sending this to the nice journal, in discussion with Tobias, I think it was Tobias, he decided to put a paragraph in that paper toward the end of the paper that said something along the lines of, because we have this augmented control landscape, then we should be able to design logic gates, information processing, that operates on femtosecond. I think in his mind, he just wanted to go past the editor. And it turns out that the editor was very interested in this idea, and the editor came back saying, you have a wonderful paper, but it would be a lot easier for me to handle it if you actually showed that last piece that you put in your paper. So then Toby closed the door of his lab and he emerged with this. And I had nothing to do with this. This was all Toby. Yeah. And so what he did was the following. This is a nanojunction. This is the nanojunction. He used the 5 micrometer nanojunction. He placed one laser right at the center, such that it will induce these real charge carriers. He placed another laser right at the interface, such that it will induce these virtual charge carriers. He controlled the amplitude of the laser fields such that the currents induced by these two components, these two of the lasers, will either cancel out, completely, or enhance one another. And then he did the following. For technical reasons, he has to plot the absolute value of the current. This is a little bit unfortunate for different phases components, and I'll walk you through this figure. So he chose the phase of A to be either pi halves or minus pi halves. If it's pi halves in this scheme, it generates a current to the right. If it's minus pi halves, it generates a current to the left. To B, he either chose it to be either pi halves or 0, because these are all interfacial effects. If it's pi halves, it does nothing, no current. Yeah. But if it's at 0, it will generate a current, and it turns out that it's in the opposite direction, something like this, such that it will cancel exactly the current due to A. And then for all these phases, he plots the current that he generates. So these are, for example, circumstances in which the two currents cancel one another and you get very little current. There are circumstances in which the current is positive and to the right. There are circumstances in which the current is negative and to the left. And then he had this insight. I can assign a logic value of 0 to phase to laser A if it has a phase of pi halves, and a logic value of 1 if it has a phase of minus pi halves. And I can do something similar with B, in which I can assign a logic value of 0 if the phase is pi halves, and a logic value of 1 if the phase is 0. And then my readout will be the current. And if the current is positive and above certain threshold, then I would say that is 1 and it's 0 otherwise. And it turns out that the only one that satisfies that is the first example. And if you read the table, then you realize that you have a logic NOR gate, with the caveat that is a logic NOR gate that operates on femtosecond timescales. So it's information processing that operates on femtosecond timescales. I don't want to fool you. Between repetitions of these experiments, you have to wait a long time. So one shot is very easy, it's very fast, but these lasers take a while to charge it. They have megahertz frequency. So it's ultra fast each of events, but then you have to wait a long time for the next shot. Okay. So this led to the idea of the Petahertz logic gate, and then we actually showed all possible NOR gate, all possible logic gates that you can construct in this. So let me summarize. I show you that the dynamics of electrons in matter can be controlled on an ultra-fast timescales with using few cycle laser pulses with the stable current envelopes. There are two contributions to that current due to what we call the real and the virtual charge carrier. And then further, you can disentangle these two contributions simply by varying the carrier envelope phase of the driving lasers. And once you have this augmented control landscape, you can develop logic gates that operate on attosecond timescales, and this can lead to this idea of petahertz electronics. So the one concept that we're really trying to push really hard in my group is the concept of lightwave electronics, in which we use femtosecond light sources to guide electrons in matter, and then do information processing and circuits and things like this. This is one something. What has this meant for me personally, as a personal story? You see, this started like the dream of a PhD student who knows it of a theory. PhD student, we don't do real things, we just do theory. That eventually led to very exciting experiments. These exciting experiments motivated better theory, and the understanding that we got from these experiments through the better theory, it led to the discovery of new physical phenomena and new technologies. So yeah, that's the story of the real and the virtual. And I think I have more to tell you, but I think it's enough to start with one story. So let me just conclude by thanking the people that actually did the work. Yeah, well, lots to say, but so this is right now my group at Rochester. The person that did the simulations that I showed is Antonio. This is an earlier generation of the group. This is a picture that we took this winter in the one day that we had snow. No, and thank you all for your attention.
All right, very good. Let me start by asking a question that you motivated in the beginning by saying you were going to do some nonlinear optics kind of thing. You will have a fundamental and second harmonic. I think here you're putting only one laser pulse in there. There's only one frequency laser pulse, right? Is it a nonlinear optics experiment? There's no nonlinear optics here.
Oh, there's a lot of nonlinear optics. So the response, the current goes to the electric field to the power of 7.
Oh, I see.
So it's really deep in the nonlinear optics.
I see. Okay.
And these pulses, they have such a wide frequency bandwidth that you get the same type of physics, no, but within one laser. I mean, if you're asking the question of whether it's better to generate currents with these few cycle laser sources with respect to the omega plus 2 omega, the few cycle laser sources are not very good at generating currents. The omega plus 2 omega are better. And my expectation is that the next generation of experiments in this direction will be ones in which they do something like omega plus 2 omega, but with few cycles.
All right, so let me open the floor for questions from the audience in this room and also from the audience on the Zoom. And if you can type on the chat or let me know if you want to ask a question, but let me start with the people in the room. Anyone has a question? Tom,
Thank you for a nice talk. When you were talking about the logic gate, and you made, I think, allusion to what might be considered an interference process because you have phases that are involved. So I guess my question is, can you simply take, constructive versus destructive interference process and call that a logic gate? Or is there something more subtle there?
Well, I mean, so you can construct logic gates in many different ways, no? There is interference. There is no real interference here. It's more like there are two currents that act in different directions, but it's not that there will be currents in one direction and currents in the other direction that at the end of the day, they will cancel one another, but it's not that the electronic waves are canceling one another, no? in this particular context. So I don't see too much subtlety. It's a matter of defining what you call your logical in and your logical out. And the phases of the laser fields encoded information in the electronic motion, and then the current would be our readout. And so those would be the natural ways to do it here. I'm not sure if I'm addressing the underlying question of your question.
I'm just curious because people have come up with all kinds of different schemes over the years, even before the current phase of quantum information, of constructing this or that new kind of logic gate. And some of them have the ability to sort of fan out and drive multiple subsequent logic gates, and others don't. And sometimes that has implications as to whether you can build a circuit out of it. So that's just why I'm curious.
So that's a wonderful question. What do we do next? I would love to see a whole circuit, to be honest. I would like to see two of these elements together. But right now, that's science fiction. That's we are not there yet. This is where we are.
I mean, can induced real or virtual carriers on one junction induce the likelihood of getting real or virtual carriers on a neighboring one? I guess that would be an interesting question.
Yeah, fascinating. I don't know. Ask me in a few years, maybe I'll make progress.
I have a question. when you started in the beginning explaining about the carrier phase, you said for this phase to be when it's 0, then the pulse is time symmetric with respect to time, and because of that, there is no real carriers are excited, right? And to me, that's a little surprising, but you're excited. You try to say because it will go both directions with positive and negative current will cancel out. Is that the idea? I mean, there, or why there is no real excitation of carriers in the case of phi equal to 0? I guess.
What we know in because this is a long convoluted way to say I don't know, but what we know is that symmetry analysis, no? And we just know from that symmetry analysis that if you look at the spatial temporal symmetries of the with equations of motion, then you realize that when you do this, this is what happens, no? But why specifically? How does it happen? Do I have a microscopic understanding of this? We don't. No? How general it is? It is general if you have a closed system and you have continuous wave type of excitation. For these few cycle laser pulses, what we know is that it applies in graphene. We know that it applies in silica, but I can construct examples in the computer in which I break this.
So, and the other question is that in both cases, whether phi 0 or phi 2, you still create a polarization. I mean, there is still a intermediate term. I mean,
so the way that I see it is that in the polarization response, for the pi/2, the intensity of the electric field of light is the same for I guess positive and negative. So whatever polarization you're getting in one direction, you will get the same polarization in the other direction. But for the phase of 0, it's more intense for one amplitude than for the other one. And then that means that you will generate bigger dipole in one direction than in the other one. But this is my better description of that process.
I'm trying to think in terms of the two-level atom picture that Joe Verley loves to have. I mean, there are there is an inversion, population inversion, which is related to electron hole excitation. So, and then there is a polarization, which is the real elementary part. So you get U, V, W kind of 3 parameters. And I would say that what you're saying in the case of when phi is 0, there's no real W. There's only U, this polarization part, complex polarization part, dipole part comes in. But in the case of phi equal to pi/2, there's a real inversion with no kind of.
Sure, but why do you suppress, for example, the momentum whenever your phase is phi halves?
Yeah. It's very interesting that the phase can play a big role.
It's suggestive that there might be another symmetry analysis that goes beyond continuous wave into the pulse excitation, but that symmetry analysis is still yet open. It's an open problem.
Looks like Wayne has his hand.
Oh yeah, Wayne. Yeah, please go ahead, Wayne.
Yeah, Ignacio, thanks for a very interesting seminar. You know, I tried some similar experiments, believe it or not, 30 years ago in Bell Labs in the early 90s, using gallium arsenide quantum wells and very high frequency strip lines, very thin structures. And one of the things that I found was that by the time I got enough virtual excitation to try to see a signal, I actually was being swamped by the real carriers that were due to multi-photon absorption, right, exciting below the band gap. So I'm wondering, is that a problem with your current experiments? How do you avoid, in other words, how do you make a pure virtual excitation below the band gap without creating a real carrier background? That's the first part of the question. The second part is, of course, back then my pulses were much longer, like 100 femtoseconds, and they weren't carrier envelope phase stabilized. But when you use these single cycle pulses, the bandwidth is huge, so you have to make sure you don't make any real excitations directly into the band gap. So I'm wondering, how do you avoid having any real carrier background when you're trying to make a virtual carrier excitation?
So in the computer, no problem, no?
That's why I asked this.
But I'll tell you how they avoid this in the experiments. So the way that the experiments are done is that they excite with these laser fields and they change the phase between realizations by a factor of pi. So say 0, pi, 0, pi. Yeah. And sure, there are many effects like the ones that you are pointing out. that will always occur because you have a complex system, you have the gold, you have the graphene, very complicated. You always generate these rectifications. But the effects that do not depend on the Carrier envelope phase will be twice as frequent than the ones that depend on the Carrier envelope phase. And then they take this magic machine that is called a lock-in amplifier, and they can separate the signal that depends on the Carrier envelope phase from everything else. So the complications that you are pointing out, they do happen, but they isolate them by this trick of varying the phase in a particular way and isolating the signal through a Carrier envelope phase.
Okay, so you still very much could have an accumulation of the real carriers in the background.
You will have them, but your signal is not sensitive to them.
Yeah, so somebody might argue that you can't really call it an instantaneous logic gate because you have to wait for those carriers to recombine, right?
You have to wait for those carriers to recombine. No, you just have to wait. You have to wait for them to go to the electrons, which is fast femtoseconds. That's fast. The problem is that whenever you're measuring charge, you need to accumulate enough charge in order to be able to have a reasonable measurement. And that requires many experiments. And so even one experiment is femtoseconds, that's fine. In order to get something measurable, you have to do millions of them. And that's not fast, no? So another interesting direction, and we'll see if this happens, is to start going to single shot measurements, because then you will be able to overcome these issues.
Okay, thank you. Good.
Any other questions from online, from on Zoom? Just please raise your hand or something, we can see you. Okay. I don't see there any questions on here by anybody else. There is one I see there, yeah.
Yeah, I was just curious. Clearly, linear polarization seems to make the most sense for this. Have you thought at all about other polarization states that is there any interesting physics to talk about in that context? I wouldn't think in your.
What do you mean by linear polarization?
Well, I was assuming that
Okay, yeah, it's a linear polarization. Yes, okay. Yes, so there are ways with these quantum materials, if you have circularly polarized light, and you can excitate, for example, what are called Valley currents, no, and things like this, or spin currents. So then you can now think about schemes with similar ideas to this, in which now you not only excite electronic currents, but actually spin currents, no, or specific spins. And this has to do with taking advantage of the additional selection rules that happen with circularly polarized light. Yeah. So this is another direction in this field.
Okay, all right. If no other question, then let's thank again Ingancio.